love to be heard.
Okay, I think I should, yeah.
That's much more aggressive now.
All right, why doesn't everyone come on in, sit down? We're going to get started here. So this next session is going to be on emerging issues in solar forecasting, and it will be chaired by Dr. Sue Ellen Haupt at NCAR, the NSF National Center for Atmospheric Research. So Sue, take it away.
Thank you, Debbie. We have an exciting session today. We're going to hear about a lot of hazards, both short-term and long-term, that impact solar and how we can forecast for them. So we're going to begin today with Thomas Haley, lead data scientist at Clean Power Research. He's going to be talking about specific applications of near-term, talking about 0 to 48 hours, probabilistic forecasting. Thomas, take it away.
Hello, I am Thomas Haley. I'm the lead data scientist at Clean Power Research. And great. So before I get started, I just want to give a shout out to the ISO dashboard managers. So my family knows this about me. It's really only a matter of time at any social event before I pull out my phone and show someone an ISO dashboard. At a house party, a photographer asked me how we would ever make renewables stable enough for growth in AI. And I showed him the ERCOT dashboard and showed that it currently charges grid scale batteries off of solar in the day and discharges in the evening at over 6 gigawatts. At a school play, a gentleman told me he had learned from experts on TV that solar power would never be able to provide more than 10 to 15% of the grid's needs. And I showed him that as we spoke, Cal ISO was currently running off of over 70% solar power. He asked me to send him the link. The world of grid scale renewable energy has changed right under everyone's noses, and nothing tells that story better than ISO dashboards. So, to the dashboard managers from all of the parents at soccer games and alumni at my college reunion, and especially my extended family, thank you. All right. So I work on the probabilistic PV power forecast at Clean Power Research with Brandon Markham and Matt Stevenson, who are also here at ESIG. So say hi to them. I will be presenting on how we created our near-term probabilistic PV power forecast and then on potential uses of the forecast. So first I'll talk about why we decided to create a forecast of GHI as a random variable. And then I'll talk about why it was important to forecast each component of irradiance jointly, and then how we use the sampled sets of GHI, DHI, and DNI to create the power forecast using a Monte Carlo method. And I'll give an example of a probabilistic forecast of a PV system, and then an example of a forecast for a curtailed system. I'll talk about two potential applications of the probabilistic forecast. The first is the ability to offer non-spinning reserves at a specific confidence. And then the second is to find the power forecast that minimizes an asymmetric cost function. So we considered three different approaches to creating a probabilistic GHI forecast. The first option was to use our existing forecast system to predict GHI and then create an additional forecast of the uncertainty of that first forecast. We already have a great deterministic forecast system, but using it as a base forecast would make it tough to iterate on improvements to our probabilistic forecast without knowing if the base forecast needed adjusting or the uncertainty part, or both. The second option was a set of quantile regression models. Quantile regression is easy to implement, but there would have been multiple models to maintain. And then for any Monte Carlo modeling of PV power, there is the issue that a function applied to a quantile output is only equal to a quantile of the function of that output if the function is strictly monotonic. But because PV power systems can clip at a hard limit, they aren't strictly monotonic. So we decided on option 3, directly forecasting GHI as a random variable. It was important that we make a few assumptions about the shape of the distribution of the GHI random variable. Basically, just limiting it from being negative or being far above clear sky GHI, but little else. So this is the kernel density estimation plot of the forecasted distribution of GHI at a site in New York State on July 18th from 9 to 9:15 a.m. And this is a 24-hour ahead forecast. The next step was to create a forecast for diffuse and direct irradiance that was also random, but one that was jointly distributed with GHI. The components of irradiance are jointly distributed because the randomness can move together. If GHI was uncertain, but then ended up being on the high end, it's likely because the clouds cleared, so DNI will be high and DHI will be low. So here is the kernel density estimation plot of the marginal distributions of GHI and DHI for the same period that we saw before. And this is the joint distribution plot of GHI and DHI. We can see that if skies are clear and GHI is high, that DHI will be low. And if skies are very cloudy, then DHI will be low as well. And if it's partly cloudy, DHI will be high because all the irradiance will be diffuse. And that's what creates this horseshoe shape. To derive the AC power of the PV system, we use a Monte Carlo approach. We run samples of the irradiance tuples through a system model to derive the distribution of AC power. In this plot, we see the GHI, DHI, and DNI, and then a plot of the normalized power. I normalized it because it was on a completely different scale and in watts, but you can see the shape next to the other ones. It looks like the DNI is going below 0 on this plot, but that's just an artifact of the kernel density estimator smoothing out these marginal distributions. There's a big peak at 0 because there's a lot of tuples where DNI is 0. So here's another set of examples from later that day at 1 p.m. Conditions are likely clear, and we can see that in the GHI. And here are the marginal distributions together on this more of a clear day. And then the joint distribution of GHI and DHI is mostly just a peak at clear sky with a tail of potential for partial clouds. So applications. The first application of probabilistic forecasts is the ability to offer non-spinning reserves at a specific confidence. So this is the longitudinal view of the forecast on July 18th at that same time, same site, multiple times. Each light blue line is one of the 9 quantiles from 10% through 90%. If a generator wanted to offer non-spinning reserves with 10% chance of deviation, they can use the 10% quantile to determine how much power to sell and how much to provide as an ancillary service reserve. Using the 1% quantile reduces the probability of deviation to 1%. Curtailed forecast. The Monte Carlo method also enables us to make curtailed probabilistic forecasts. This is a forecast for the system curtailed at 40 megawatts. So you can see the uncertainty in production collapses in the middle of the day because we're hitting that limit. I think these timestamps are in UTC. Sorry about that. This leads to an interesting case where the mean of the distribution is briefly below the 10% quantile. Okay, and now we'll talk about minimizing expected cost. This is the most exciting part of the talk, I think. Sometimes the cost of an under forecast is less than the cost of an over forecast. In that case, it is a good idea to bet low or to lower the forecast to be, quote, more conservative. But how much exactly? What is too conservative? The distribution of AC power can be used to derive a single forecast that minimizes expected cost. So the top graph here shows the forecasted distribution of AC power discretized to 20 possible outcomes associated with 20 probabilities. So this is like a discrete approximation of the PDF of AC power. The bottom graph shows a cost function that has 10 megawatt dead band that doesn't penalize any forecast that is correct within 5 megawatts in either direction. Beyond the dead band, over forecasts are penalized twice as much as under forecast. The cost function is shown here for a forecast at 20 megawatts. So if the actual production is 10 megawatts, which means that we over forecasted by 10 megawatts, it'll cost us twice as much as if the actual production is 30 megawatts, which means we were undershooting our forecast by 10 megawatts. So the bottom graph here shows the expected cost of each actual production level. if we chose a forecast of 20 megawatts. It's all the probabilities of the top graph multiplied by the costs on the bottom graph, middle graph. Adding up the area under the curve in the bottom graph gives us the total expected cost for that forecast at 20 megawatts. And by scanning over multiple forecast amounts, we can see in the bottom graph the total expected cost for each forecast amount. When the animation ends, we can see the forecast minimizes the cost function is 15.58 megawatts. Probabilistic forecasts make it possible to dynamically calculate the forecast that minimizes costs given a cost function, even a kind of a funny asymmetric cost function with deadbands. Thank you.
Great talk, Thomas, and perfect timing. Does anybody have a clarifying question? Okay, why don't you go to the mic?
Thanks, Thomas. Very interesting. Joe Roberts, ISO New England. I don't know if I just missed it, but you kind of went right into where you're getting your component irradiance values and the model of them. How do you actually tie that into the physical reality that day? Is it model-derived actual irradiance that you're starting with like a point forecast and then building out your distribution from there? How do you kind of move that from what you have to that probabilistic space?
Oh, yes, that makes sense. Okay, so how are we getting like the GHI, DNI, and turning those into, we're using a Monte Carlo method. So we sample it hundreds and hundreds of times. The what? They're sampling the irradiance. So we'll say, give me a jointly distributed set of GHI, DHI, and DNI. And then the model, the random variable model they say, okay, here it is. And then we say, great, do it hundreds more times. And then we run them all through the power model. So I think you raise a really good point. One of the things that we're really sensitive to is how that power model works. And so we want to make sure that, and that's kind of where the rubber meets the road, is making sure that our power model accurately represents what's really going on in a PV power plant. And that's a hugely important part of the process that I didn't go into in this talk.
Okay, let's move on after that great innovative way of calculating probabilistic solar production. Now we're going to move on to hail with Daran Rife, who is principal scientist for energy systems at DNV. And title of his talk is Bigger, Fewer, and Further North, How Climate Change is Redrawing the Solar Hail Risk Map. Daran.
Thanks. Will this work if I do it this way? Oh, I like that much better. Well, so the headline title of my talk is actually a good one-sentence summary of where the science lands right now on the future of hail. And I'll talk more about that in this talk and what the implications are for solar PV plants. So here are the stakes. In Texas alone, and over the last several years, there's been over $600 million of hail loss for solar PV plants. And one of the most notable is the Fighting Jays solar project, which some of you may be familiar with, experienced over 100 millimeter hail back in March of 2024 and sustained very significant damage. Now, one of the challenges is that the current IEC testing standard says test against a 25 millimeter hailstone, which is completely inadequate, obviously, for the US hail market. Those numbers were derived for European climates. Now, fortunately, the major test labs that we work with at DNV, their minimum size is 50 millimeters, but that standard definitely needs to be updated. And what I'm going to show you in the next couple of slides is that there are multiple independent studies that show that the risk is becoming increasingly significant over the next decades through the end of the century. So what is driving these projected changes in the hail risk? There's two primary mechanisms. The first is in our warming world, this allows the atmosphere to hold more moisture, which then fuels stronger thunderstorm updrafts and larger hail. Now, at the same time, the melting level in the atmosphere is actually increasing in altitude. So what that's effectively doing is filtering out the smallest stones, so only the largest stones reach the ground. And the net impact of all that is that there'll be fewer events, but when they happen, they'll be larger and far more energetic. Now, a very recent study that was published just a few weeks ago in Nature, they ran a very large ensemble of hailstorm simulations under various climate scenarios. And what they found was a minimum of 32% increase in hailstones greater than 30 millimeters globally. And that's even under moderate warming scenarios. Well, it turns out that the shifts that we're seeing in that are projected in hail are already measurable. And I'm presenting here two lines of evidence. So the first is a study that was published back in 2019. And what they found was large hail favoring environments are increasing by 2 to 4 days per decade since 1979 in the central and the eastern US. So the environmental precondition for these really large hailstones is now common in places where it was never common before. Now, another study, completely independent, published in 2024, looked at the NOAA storm data. This is the actual hail reports that hit the ground. And they looked at the data from 2000 to 2022. And what they found is the hail risk centroid, that geographic centroid of the hail risk in the eastern US has actually migrated northward by about 5 degrees over that time period. And so states in these areas are now experiencing hail on scales that they've never seen before historically. So the hail risk, in spite of what you've just seen, the hail risk still is primarily in the central US, places like Texas, the Great Plains. But the emerging story is, as you've seen on the previous slides, is the Northeast US. Right? The hail risk is migrating into these regions. And what this means is all the solar plants that have been either designed or built over the last decade have not accounted for the shifts that are already occurring. And these are places where there are major build-outs happening. So the fastest growing exposure is now the core Midwest and the Mid-Atlantic. So here are the implications. As I've shown, the design standard, the IZ design standard, is obviously woefully inadequate for the US market. That needs to be updated. That's not going to happen soon. IEC takes a long time to make its updates. And the other point is that most of the providers of hail risk data, so hail return periods and so forth, rely entirely on historical data. And given the changes that we're already seeing, that is going to understate the future risk that we're seeing in the projections, and not only in the projections, but in the historical data. And because the geographic region of hail risk is shifting northward, this means that we're developing right in the path where the greatest risk is shifting towards. So let's give a couple of examples of what that looks like to help maybe give this a bit more context. There's a couple of recent examples. So first example is from Indiana. This is back in March of 2026. There was a massive supercell thunderstorm outbreak actually over many of the northern states, but by the time it reached the Indiana, northern Illinois border, it was dropping hail 2 to 4 inches, which is quite record breaking. There happened to be a solar plant right in the direct path of this storm, and it sustained significant damage. Now, Indiana does not historically have much hail loss for solar PV information. So the insurers have no empirical data from which to base their models or their risk profiles. Now, the second example is North Carolina. So KWH Analytics recently did a study, and what they found was between 2020 and 2024, about 19% of the hail loss events occurred in North Carolina, a state not historically considered high risk. And it turns out, my slide is a bit out of date. I checked this yesterday. North Carolina is currently the 4th largest installed capacity of solar in the US. So here's a place where we're seeing massive losses, but historically has not been considered a high risk. So places like Texas have given us this crash course in how to deal with this over the last couple of years. And the existing tools and models that are out there are based on Texas and Great Plains data, but these are not appropriate for places like Indiana, New Jersey, North Carolina, where the character of storms is just typically much less vigorous than it is in Texas, but the threat is shifting northward. So this is why physics-based modeling is really needed in these areas. So to help address this issue, DNV has developed an end-to-end rigorous hail risk modeling framework, and it is based on empirical methods. They're peer-reviewed. It's based on actual real-world hail data and published methods. Now, I'm only going to be able to show you one aspect of that because I don't have much time, and that is the hail damage swath emulator. Now, for those of you that are not familiar with an emulator, it's a weather emulator in this case. It's simply a statistical model that generates realistic scenarios based on statistical characteristics of historical data, in this case, damage swaths. So we're relying on a peer-reviewed published data set of hail damage swaths over a 20-year period. And the way that the emulator works is it generates 10,000 synthetic swaths. They range from anywhere from 5 to 100 kilometers in length on average, and anywhere from 5 to 20 kilometers wide on average. There are some that are larger, but those tend to be more rare in the data set. We randomly place these within 25 kilometers of the project. They're oriented from a north to a south direction because in the US, storms tend to move from a westerly direction, okay? And what we're looking at here is a sample of those synthetic swaths for a 100 megawatt and a 600 megawatt footprint project. So the red swaths are the ones that make a direct strike. What you see just from the sample of swaths is most of the storms miss the project entirely. But when they do, there's significant overlap, meaning that there are big consequences. So let's have a look at some numbers and see what that looks like. Now, here's a case study for a 600 megawatt solar project. Okay, and there's two numbers that basically tell the story here. So let's focus on the left first. The left is what is the probability of your project, 600 megawatt project in this case, being hit by one of these storms from the emulator. And it's really low. It's about 8%, 1 in 12 chance. Pretty encouraging until you look at the number on the right-hand side of the screen. And this is, if I do get hit, how much of my project is going to be impacted? And in this case, it's about 62% of the project is going to be impacted. So low probability, high consequence. And this matches really well with what we're seeing in the industry loss data that we have available to us. So just a couple of key takeaways before we move on to a couple of things on financing. As we said, there's a low probability of being hit, but a high consequence. This matches very well with the loss data that we have available to us. And the other important point that I'm going to talk a little bit more on the next slides is that insurers are now starting to reward if you have demonstrated risk reduction methods, including technology and the human in the loop. So the question, of course, is not, do I manage the risk or not? You have to manage the risk, but you have to understand three things, and they're listed here. The first is you need to know your probable maximum loss and need a credible probable maximum loss. If you go into a conversation with your PML of 99% destroying 80% of your project, that's a very different conversation than if it destroys 20% of your project. So you need somebody who's going to give you a credible PML. You also need to know what kind of insurance coverage you can get. Not everybody's willing to offer insurance coverage on these things. And if they do, it's often very expensive. And thirdly, you need to understand the capital expenditure. Buying hail-resistant equipment, thicker glass, trackers that allow defensive stow at high angle, that is upfront cost. So you need to know all three of these things to determine which set or which configuration makes the most financial sense for your project. So I'm going to close with this. Looking around the room, all the lenders, developers, owners, operators, or asset managers, how many of you can answer these 5 questions right now for a project you're actively working on? That's a bit of a rhetorical question, but the key points here are that you need to understand your risk. You need to understand what, if any, insurance coverage you can get and how much it's going to cost. And you need to understand that capital expenditure for buying the technologies that allow you to mitigate the risk. So I'm going to stop there, and I'll be happy to take questions during the Q&A session. Thanks very much for your time.
Okay, very interesting, Daran. Any clarifying questions, Jeff?
Really, a clarifying question. How difficult is it to get insurance now for a farm, and has it become more difficult over time?
That's a really great question. So the market has really matured in the last couple of years. So 2 years ago, ain't happening. If you were in the hell alley, they just said red flag, red flag, red flag, and it was almost cost prohibitive. So what a lot of developers were doing was self-insurance, like tucking away, okay, we're going to set aside X million dollars or set aside X amount of equipment to do this. Recently, we're starting to actually see, and I can't remember the name of the two insurance companies that are doing this, have offered for demonstrable technology mitigation, as well as a human in the loop program where you're actively monitoring the weather and you do defensive stow drills, et cetera, et cetera. They've actually offered a pretty substantial discount. We've been told by the insurance company, they didn't tell us, of course, what that number was, because that's always confidential, but I think it's becoming easier. But there's so little loss data on solar PV across the country that the insurance companies just like have no idea what to do with it, and so it's just considered high risk. So we're hoping that the industry's made tremendous strides in the last couple of years on mitigation after all we had so many bad losses several years ago, and I think the insurance industry is really starting to recognize that. So I think it's getting easier, but I think it's still a bit of a challenge.
Should we hold? Is it one that can hold till the Q&A? Okay, you can be first. Okay, now we're going to change our events. Peter Zadow, Senior Meteorologist for Energy and Meteo Systems in Germany, is going to talk about extreme event solar forecasting, wildfires, storms, and snow.
Yeah, hello, I'm Peter Zadow, hard to pronounce, no worries, even for Germans. So I will be talking today a bit more on the forecast perspective. So what are we doing to forecast extreme events in specific regarding wildfires and snow? Most of you have been here yesterday, so you know this slide, Lars presented it already, so I'll skip over it to have a bit more time for my actual presentation. First, we do specific scenario forecasts. So for multiple extreme events, we don't just rely on the normal parameters we get out of numerical weather prediction model, but we do a specific scenario forecast for the individual event. So first starting, how do we normally do our forecast? We take various parameters from the numerical weather prediction models, multiple at any time, and combine them with additional data sources such as live power measurements or satellite data, whatever we have available regarding the specific site, and do a forecast from up to the next 5 minutes to next 15 days, and have this forecast, of course, always present for each individual site. Now, looking at the scenarios, we take the same data set more or less, so same numerical weather prediction models, but different parameters, and same additional data sources such as live power measurements or satellite data, and derive a specific correction for the underlying extreme event. So in this case, a huge snowstorm is coming up, so we derive a specific correction based on the data we get from the numerical weather predictions. And the scenarios are calculated for each individual site. So every site has a forecast with and without snow correction, so you can derive the impact of the extreme event on a site-specific basis, which then afterwards can be aggregated on regional levels. However, we believe that a good forecast only can take you so far, because most of you, at least in the American market, are also interested what is the risk associated with my forecast. So how far can I go below or above what the forecast is at any point in time? So what we are doing is we provide additional situation awareness products, mostly in form of reports, which are sent out automatically to all of our customers, which have a condensed overview of an upcoming extreme event. So on the right-hand side, you see such an example of a report from AESA, who were kind enough allowing us to share the data here. Now for a smoke event, which will happen more or less 4 days from the date the report was sent out. It first always gives an information about the worst case scenario. So when is the event supposed to happen, and how large is the event going to be? So the numbers are quite small, but this is a smoke event reducing the PV power by about 200 megawatts. So still quite significantly. And apart from this worst case, we also have this temporal evolution. So when will this event happen, and how strong will it happen during the next days? Both, of course, in a tabular format, but also in form of time series. These reports are always triggered based on customizable thresholds, so every customer can decide when they want to receive a report, because if we send it out every day, no one will read it. Like if you get an email every day, you won't look at it. So it's supposed to be only there if you should be taking it into account into your plan. Now I will go into a bit more detail for 2 of our examples. So first, staying with our smoke event. Again, on the right-hand side, the report, which is based on our internal aerosol correction, which is, among other, based on weather model output. And I've included a figure from the vertically integrated smoke from the HRR, also 4 days out. So we see was a huge wildfire in southern Canada, having smoke across southern Canada and northern US. And if we go a bit further down the timeline, so now we're in the intraday, same map, smoke was shifted a bit further east, but still prevalent above southern Canada and middle of the northern US. And on the right-hand side, you see an updated smoke report. So now we're in the intraday, you see that the smoke will impact the following 24 hours. And now by up to 250 megawatts reduction just for the IESO region, which has an installed capacity of 2.5 gigawatts, so 10% of the installed DC capacity reduced just due to smoke. And this is always given out every day, so any customer can plan in accordance how much energy they will have available from solar plants. But this is not only present in our situation awareness reports, but also in our forecast directly. So here I've shown you forecast and measurements from the day of the reports. In the solid orange line, that's our forecast with the smoke correction, while the dashed orange line is the one without, and the black line is the measurements. What you can see is that the forecast was reduced by 8% of the installed capacity, which is tuned a bit more conservative than what you've seen in the report, because the report is supposed to give a worst case estimation. So what really could happen, while the forecast is a bit more best guess what we believe will happen during this time. And at least during the noon hours, we see a quite good fit. So during noon hours, our smoke correction works quite well. So we have a good estimation of how the aerosols reduce the PV production. However, we see that especially during morning hours, but also during evening hours, our correction is still a bit too weak. So we're still tuning our correction to better incorporate those effects on the PV production, which is partly due to also, we believe, the tracked panels which are prevalent in the US. And this correction is already operative in all of our US forecasts, because it's much more prevalent in the US than in Europe. We don't have that much smoke there. The second part is snow. So again, we have a report, again from IESO, so southern Canada. Now a snowstorm just this January, so 6th of January, where we had a huge snow event across nearly all of the farms from IESO. Again, 2.5 gigawatts installed capacity and 500 megawatts reduced just due to snow, which was 84% of the forecasted PV power. So yeah, if the worst case would have happened, you basically didn't have any solar energy anymore, which is quite significant, and we want to make you aware of that. This report is only triggered in the day ahead and intraday, because it's much harder to predict the impact of snow than it is for smoke generally. Again, this is a worst case estimate, so not necessarily what we believe will happen, but we want to make you aware that it could happen. So how does it look like in the forecast? Again, solid line is the forecast with snow correction, while the dashed line is the one without, and the black are the measurements. And here we see a bit different behavior, but it's again based on our internal snow correction. It has an impact of 16% of the installed capacity, so quite significant, not as strong as the worst case, but still significantly. And it has a really good fit during the snowfall. So it snowed nearly half a day there, and during the snowfall itself, we saw that the reduction was nearly as strong as we predicted. However, once the snow stops falling, the snow slides off nearly instantly in the US. So what we see in Europe, snow can stay on non-tracked panels for weeks, while in the US it takes less than an hour to completely be snow-free, mostly due to the tilt mechanisms most of the tracked panels have. And that means that we are basically snow-free instantly after the snow stops falling. And this has a huge problem for the forecast, because predicting when snow is falling and when it's stopping is quite difficult. And since the impact is quite large, we see that right afterwards it shoots up back to our normal forecast. We are a bit conservative in applying this method directly on the forecast. We have a method to use the live data feed to correct our snow correction, but it's still, especially in the day ahead, a bit problematic. So what is coming up next? We see that there is a rising importance of solar energy in the US. So we see buildup of the PV plants, especially in the northern US in the last years. And there's also a higher risk with wildfires associated and snowstorms. So we believe that the impact of those extreme events, which are not that extreme because they are quite frequent, will rise in the next years. Further, we are tuning our scenarios a bit more through the US market, so especially looking at tracked panels and using more of the regional models present in the US to derive better correction to our normal forecast. And lastly, we will be looking at machine learning for enhanced forecast accuracy, especially looking at pattern recognition, because we have a lot of data and we have a lot of both measurements and weather data from models. So we're trying to use machine learning to have pattern recognition and also use a data-driven training to derive better correction coefficients. And this is currently in progress and hopefully available in the next years. So thank you for your attention. And if you have any questions, feel free to write me a mail or ask me during this conference.
Hey, thank you, Peter. Clarifying question, quick. Okay, Jeff.
You had mentioned about in the US, it's different that the snow comes off the panels. And I can tell you from firsthand experience, at least in the eastern US and New York, last winter, there's a solar farm a couple of miles from less than a mile from my house. And we had a lot of snow, a lot of ice, and that snow and ice stayed on those panels for weeks. So something to consider that it's a little different kind of regime in the northeastern US, let's say, than further west, where you can get heavy wet snow that can then freeze. And then if you have an extended period of cold weather like we had, that doesn't go anywhere.
Yeah, maybe just shortly to that, we also know that there are preventing methods, like there's specially built PV plants who are supposed to get rid of the snow very fast, but it's like the data is not there yet. Like most customers don't know which farms those have this prevention method, so it's a bit hard to predict, but yeah, we're looking at it.
Mm-hmm. Okay, moving on. We're going to move into more winter weather with Leigh Munchak, Senior Meteorological Data Engineer at Vaisala, talking about probabilistic forecasting of winter weather impacts on solar power production. Leigh, you have the floor.
All right, so thank you, Sue, for scheduling me after Peter, because he gave a really great overview of how winter weather can affect solar power production, along with a lot of other different perils. So I'm going to be focusing on just winter weather. Here's my one quick slide on renewable energy forecasting at Vaisala. We offer wind and solar forecasts for every RTO in the United States, and we're expanding into Europe. And we also forecast wind and solar power generation for bespoke locations from clients. And those are the only ones we're using our probabilistic solar approach right now. So I'll focus on that. And we really chose to focus on winter storms because they pose some unique challenges to balancing the grid. Here I've plotted the load during Winter Storm Elliott and in PJM and Winter Storm Uri in ERCOT. And you can see during the storm, the load was increased about 50% compared to the 10-year baseline. And that's just because winter storms are associated with pretty extreme cold. So you've got increased demand, and at the same time, you have decreased generation, not just from solar, which is what I'm going to talk about, but also when there's icing on wind turbines, they will often go down. There can be logistics disruptions for natural gas deliveries. So all of this leads to really tight operating conditions. So we need accurate forecasts, but we also want a long lead time. We want some characterization of the likelihood and maybe predicted the severity of the event as well. So when I talk about winter weather, I'm actually really focusing on two sub-perils. The first is snowfall, which reduces irradiance on the panels. And the second is ice and freezing rain. Now ice is clear. It actually doesn't prevent solar generation, but we've seen many instances where infrastructure can actually be damaged, and it can take a solar farm offline completely. And here's just one example of how a winter storm impacted a solar farm. This was in Texas during Uri. And the first few days of this event, I should say, this is a stitched day ahead forecast. So this is the morning forecast that's valid the next day. And during the first part of this period, it was dry but cloudy. So we predicted low to moderate generation, that's in the blue, and it fairly well matched the observations in red. On the 13th, there was a light freezing rain event. Again, ice is clear. There was no impact on the power generation. It was a good forecast, and because it was light, there was no damage. And then there was an overnight snow event. This clouds associated with the snow moved out, so we were predicting quite high generation, but there was a thin layer of snow on the panels, about an inch. So that was reducing, but not eliminating the generation. Now compare that to 3 days later, there was a quite heavy snow event, a few inches. And you can see there was still some clouds in the area because we were predicting like moderate generation, but due to the snow, there was almost no power coming out of this farm. So this was a pretty severe over forecast bias. And then the next day we observed what Peter talked about, this snow sliding event. In the morning, the snow was sitting on the panels. We see almost no generation. This is a single axis tracker farm. It's also a very clear sky day. So those panels are heating up, they're tilting, and at some point the snow just slides off all at once and the generation shoots up. And you can see that afternoon and even the next day, we're actually now have an under forecast bias because that snow on the ground is enhancing the albedo. It's sending more radiation back up to the panels, and that's actually being captured as additional generation. So we saw that case example and a lot more that basically said, we know that this peril is impacting solar generation, and we know that these kinds of forecasts are really important for operations. We're going to try to develop something that's going to solve this problem. So here's a little overview of our methodology. Basically, we make our solar forecast exactly as we always have. I've called that the original forecast, the snow off forecast, and that's shown as in teal. And then we have an entirely separate module that deals with the winter weather. We take in NWP forecasts of winter weather, we calculate the power reduction due to those perils, and then we add it back to the original forecast to create what I call the snow on forecast. And we can either deliver the snow on forecast or deliver the power. We can deliver both the snow off and snow on. And I kind of like that because it also gives some idea of why we're seeing low power generation. Because like you saw on the last slide, a cloudy day and a snowy day can look pretty much alike in terms of generation. But we have a lot of confidence in the cloud forecast, and we have less confidence in the snow forecast. So this gives the operator kind of another dimension of information to use the forecast. So I said the first step is to take in the NWP forecast data of winter weather. Now, I live in DC. That's an area that's pretty famous for snow busts. I've got a picture here of Jim Cantori standing in front of the Capitol building. We were supposed to get 13 inches of snow and it was 34 degrees and raining. So I'm a big believer in ensemble approaches, especially for winter weather forecasting. It really shows the range of what's possible instead of locking on to one or two deterministic models. That's not going to give you a lot of information about your different scenarios. We looked at a lot of different sources of information. We ended up deciding on the ECMWF ensemble system. I liked it because it's got a long forecast length, it's global, you've got 50 members, and also the winter weather variables are quite good. The categorical precip is actually quite refined. So it'll tell you whether it's freezing rain or sleet or snowfall. And that's actually not something you get from every NWP model. So then we run all 50 ensemble members through a snowfall impact module. It's basically a physically based snow soiling algorithm with snow sliding, along with a correction algorithm from the observations, because like Peter said, you don't exactly know when the snow slides off. We run that, we calculate the power reduction for all 50 members, and from there we calculate a worst case, that's the most severe ensemble member, along with the most likely, that's the median, and apply that back to the power forecast, and you can kind of see what reduction occurred due to snowfall. We do the same thing for icing. Since this isn't going to reduce the generation, we basically set a threshold. And if the icing amount is above the threshold, we take a farm out of service. It's either 100% generation or 0. And again, you see it, we're doing it for the most severe ensemble member, that's our worst case, and the median, which is our most likely. And then we turn that ensemble information into a quantification of risk. Basically, we have 50 members that all have a quantitative estimation of the power reduction. We can see what fraction of those ensemble members are predicting an impact and turn that into a 0 to 100% probability. And we also condense that into a categories, high risk, low risk, very low risk, for those who need to ingest that data a little more qualitatively. So here I've just shown some attempts at validation. Honestly, it's really hard to validate extreme events because they are infrequent. We've done it mostly via case studies, and here's one of those case studies. This is a forecast that was issued January 21st in 2025. The first day of the forecast is showing basically just clouds. The second day is showing an overnight snowfall event. Our original forecast is in the blue, it's showing pretty high fleet level generation. Our most likely scenarios in the purple dashed line, and our observed power generation is in the black line. And the most likely scenario actually matched the observations pretty well. Of course, the worst case did not, but that's giving you an extra element to prepare for, even though you don't really expect it to validate. We also offer impact alerting, twice a day emails if there is an impact expected, because this system is running every day, every hour. Most of the time it's 0 for most farms. And basically if we do see an impact, then we'll go ahead and send out an email. But it's a really nice way for an operator to basically say, oh, wow, okay, 5 days out, there's a very low risk of a very high impact event. I'm not going to change my operation strategy, but I'm going to start paying attention. I'm going to watch how this forecast evolves. And then by day 3 or 4, you have some better ideas of what's going on with still some time to prepare. And then day 1 comes out and you're starting to get a really good quantitative understanding. And so finally, I just wanted to put these forecasts in a bit of a broader context. We chose to quantitatively forecast the risk of winter weather on solar power production, basically for 2 reasons. 1, the science is really well understood. And 2, the meteorology behind winter storms supports it. These are large-scale events. They impact multiple states at once. They're long duration, and they can be seen from several days out. There's other perils, like Daran talked about the importance of hail. Those are maybe more suited for a proactive alerting approach rather than quantification, because the meteorology behind them different. The lead time is minutes, not days. The impact is farm, not fleet. And so there's different approaches for different perils, and I'm sure lots of people have a lot of opinions on how best to use these forecasts.
Thank you, Leigh. Any clarifying questions before we move on?
Hi, Leigh. Joe Mulhern, PJM. How do you make that translation from, well, I guess into the high, medium, and low risk? Is that percentile based? Is it, you just kind of explain what the approach is?
Sure. So the first step of the quantification of likelihood is basically converting those 50 ensemble members into a 0 to 100 scale. So that's quantitative. That's if 30 members show an impact, that's a 60% risk. And then the conversion to a qualitative scale is really, we picked a few thresholds. It's like, I'd have to double check, but it's something like above 50% we call high risk, 30 to 50 is medium. So that's just a mapping essentially from that quantitative risk information into a qualitative category.
Okay, thank you. We're going to shift gears a little bit. Jared Leigh, who's a scientist at NSF NCAR, is going to talk about Dunkelfloats. Sorry, those of you who speak German. And solar drought potential in North America. Jared, you have the floor.
All right, thanks, Sue. So we'll be talking some about Dunkelflaute, and before I begin, I just want to acknowledge my co-authors because I definitely did not do this work all on my own. It was supposed to be a picture of solar panels, not a storm, but oh well, looks pretty. So this audience knows, I expect, what renewable energy droughts are. Just again, it's a major shortfall in the expected renewable energy generation for that time of year due to weather variability. The short duration events, they can usually be mitigated through battery storage, dispatchable generation, or transmission from other regions. But then longer duration events that might last a day or more are a lot more difficult to cover, especially when both wind and solar are experiencing concurrent shortfalls. And so most of these drought events are less than 1 week, but some can last several months, such as summer 2021 over Europe. There are a few different ways of defining a drought. The two main categories of ways are duration given intensity. So if you pick a certain intensity of drought, how long will that last? And that's very common in the literature. And the other common way is intensity given duration. So if you pick a certain duration of event, how intense is it? Our work really builds on especially 3 papers by Jim Wilsack, retired from NOAA, from 2024 and 2025. I'm not going to go into detail in these papers, but the main thing is he took the ERA 5 reanalysis, which is very commonly used in this industry. And while it's commonly used as basically truth, like any other modeling product, and ERA 5 is itself a modeling product, it also has biases and errors that you should be aware of too. And so what Jim and his group did, they bias corrected the ERA 5 and found that the resulting solar and wind capacity factors match much closer to the observations than did the raw ERA 5. And just to highlight some changes in the ERA 5 bias corrected from 1959 to 2020 across most of the US. They're showing a slight decline in solar capacity factor over this time period, with maybe some slight increases over the West. But then also looking at the different durations of these events from 1 day out to 90 days, that changes the severity of the potential droughts or floods that might happen. And so we're going to be using these curves to basically define what is our threshold for a drought of duration 7 days, for instance. So this is how we're building on that work. And so what are we doing? And so we've been running WRF at 12-kilometer grid spacing over all of North America, so this outer yellow box, for 40 years of historical climate and also 40 years of future climate. So in this presentation, we only have the 30 years of future done yet. The last 10 years are being run right now. And so it's forced by the MPI low resolution climate model. We do include land use and land cover and also aerosol changes through this time period. And it's following the SSP 5 8.5 greenhouse gas concentration pathway. So the output of this will follow the conventions of the NA Cordex, the coordinated regional climate downscaling experiment. And we have 1 hourly output for renewable energy relevant variables, whereas most of the other climate models in the Cordex family don't really have renewable energy relevant variables. So that's one place where we are filling a need. And all of this data will be made publicly available. So how do these WRF experiments compare to ERA 5? So again, I'll just focus mainly on GHI since this is a solar session. So compared to the raw ERA 5, this is not bias corrected, it's raw ERA 5. ERA 5 is higher than the WRF simulations in the eastern US, whereas the WRF simulations are higher in the western US. But we also know that ERA 5, raw ERA 5, has about a 20% bias in GHI over temperature at higher temperature and more humid sites in the eastern US. But then looking at the future changes from the historical, we also see for GHI over most of the US, except for the high plains, we generally see a decrease in GHI in this WRF simulation from the historical to the future. So in order to make this, first we convert all the weather outputs into a capacity factor. And so how I did that is using the pvlib Python library, set up a single 5 megawatt fixed tilt PV array at every grid point, with the fixed tilt equal to the latitude. And so then every hour we generate a capacity factor, an estimated capacity factor coming out of that. And so this is showing across the whole domain the 41-year mean solar capacity factor from the historical period. And this is showing then the historical and the future. So I'm going to rock back and forth. If you look on the right, it'll rock back and forth between the historical and the future, historical and the future. So what's happening is that in these WRF simulations, for the future time period, we are seeing in general a reduction in solar capacity factor over most of North America. So how are we defining the drought object? So we're using a tool called MODE, the method for object-based diagnostic evaluation. It is one of the tools in the model evaluation tools verification toolkit that's developed and maintained by NSF NCAR, which is also used operationally at several national centers. There's a big user community for MET and MET+. And so MODE was developed as a tool to enable assessment of objects beyond just probability of detection and false alarm ratio. And it was initially developed to do precipitation verification. Like for instance, if a squall line is coming through and it's just delayed by an hour, but otherwise looks good, that can still be a good forecast because the objects still look similar to each other. And so with this object-based verification, we can get at characteristics of the objects, like the object area, intensity, location, the axis angle, things like that. And we can build climatological distributions of these objects over decades of simulations. So again, this is just a graphic to show you have some output at some threshold and you apply a convolution radius to basically smooth out the hard edges of the field a bit, and that defines your object. And so this has a bunch of details about our initial first cut at how we're defining the objects. So here in the middle, we have a summer case, and on the right is a winter case. So the fields are these super colorful fields in the top row. And then this middle row is showing where MODE is identifying the objects. So for instance, for the summer case, in the right column, we have the ERA 5 bias corrected. You can see where there's a very low area of 7-day solar capacity factor. It picks out an object there. Now I'll just also note that the WRF simulations are not simulating the weather of the day, whereas the ERA 5 is. And so we don't expect a one-to-one correspondence between where the drought objects are located. We're just trying to build climatologies and see how similar are the distributions over time. And so for this first cut, we are applying a single domain-wide capacity factor threshold We will change that as we refine our analysis, but that's what we're doing for right now. And this table went way huge, the transition from Mac to Windows. But anyway, so basically the number of objects. So comparing WRF historical to the ERA 5 bias corrected, we're seeing a lot fewer objects in our WRF simulations with a much smaller mean area, but also somewhat more extreme in terms of the capacity factor. So fewer objects, smaller objects, but more extreme. The other thing to note here, going from the historical to the future period, we are seeing an increase, at least for this, again, this very first cut of defining 7-day long drought objects for solar. We are seeing an increase in the number of objects, but they're smaller. The intensity is about the same, so we're seeing smaller but more numerous drought objects. So this is all very preliminary, so please don't say NCAR right now that NCAR says this is happening. We're in the process of doing this research and we will refine this. But just looking at the decades, breaking down the number of objects per decade, interestingly, for our WRF simulations here at the bottom, we're seeing slight increase over time, over the decades, which is basically the opposite of the trend in the ERA 5. So we're trying to figure that out, what that means. But as we refine our drought analysis, we'll see if that stays true. But stitching together the historical and the future trends, my eye puts together a nice linear trend over this time period. So we don't have any simulations in these middle decades, but it does seem to be that there's an indication of an increase in solar drought potential as we move forward, at least with this particular scenario. So just again, as a summary, we have 40 years of historical and soon 40 years of future 12-kilometer WRF regional climate simulations. And we're defining drought objects for wind, solar, and eventually combined wind and solar objects, and then examining how the climatologies of those objects change. And so we have several different, we're going to be refining our analysis and looking at several different thresholds or durations rather, doing rolling means rather than consecutive periods. So we're going to be refining this analysis and making it better. If you have any questions, feel free to contact me or find me after the break.
Okay, thank you, Jared. Now, before we get into general questions, anything clarifying for Jared?
Yeah, thanks, Jared. When you were flipping back and forth between the maps, was that the capacity factor reduction for the 7-day Dunkelflaute, or was that just in general?
So those average maps are looking at every hour of capacity factor, the mean over 41 years for the historical period and 31 years for the future period that we have so far.
And the future period was modeled at the SSP
585.
8.5 or
8.5, yes.
Okay. In that, what was the rationale for that? I hear that that's actually going to be downgraded in a couple months at the next meeting.
So the rationale for choosing that, so if for the Cordex simulation, so there are different groups all around the world that run these simulations. And so there's basically a grid of what is the driving climate model, and then what is the SSP pathway that you're simulating for emissions. And so no one had yet simulated this MPI low resolution with SSP 5 8.5. So we're basically helping the community by